All right. Hey everyone, I'm Stephen Slaughter and I'm today's host for the USGS Landslide Hazard Seminar. This meeting is co-organized with contributions from Matt Thomas and Jamie Kostelink, who are in the field today, and myself. During today's presentation, please remember to keep your microphones muted and your video turned off. We ask the speakers to reserve 10 minutes before the top of the hour for questions, so you can submit your questions via the chat function, or following the presentation, use the raise your hand feature to ask questions using the microphone and camera. Today's speaker is Nick Mathews from the U.S. Geological Survey. Nick started in September of 2021 in a Mendenhall postdoctoral research fellowship with the Landslide Hazards program here in Golden, Colorado. And Nick will research post-fire landslide hazards. However, before joining the USGS, Nick completed his PhD and MS in civil engineering at Oregon State University, where he worked with Ben Lachinsky on developing new models to assess rainfall and seismically triggered landslides at both the local and regional scale. Born and raised in Anchorage, he is now a recent transplant to Colorado. And Nick had told me that he's looking forward to playing in the Rocky Mountains and sampling the many bakeries that flank the steep and rugged slopes. So to all the Coloradans out there, please email Nick and me your mountain adjacent bakery recommendations. So Nick, welcome. The virtual stage is yours.
Okay, thanks, Stephen. Yeah, so I'm Nick, and you know, I've seen a lot of really excellent presentations as part of the seminar series, so I am both humbled and thrilled to be here giving a presentation on a regional scale, three-dimensional susceptibility model that I developed with my PhD advisor, Ben Lachinsky, for enhanced evaluation of rainfall and seismically induced landsliding.
Hey, Nick, your microphone is turned off.
Oh gosh. Okay, let's start.
We have a hot mic out there too. Let me see if I can mute this person. Okay, go ahead. Sorry.
Amateur mistake. Okay, let's start over. Yeah, so thanks for the intro. I'm Nick, and yeah, I've seen a lot of great presentations as part of the seminar series. So I'm both humbled and thrilled to be here today. And I'll be talking about a regional scale three-dimensional susceptibility model that I developed with my PhD advisor, Ben Lachinsky, for the enhanced evaluation of rainfall and seismically induced landsliding. So I'll start by just framing why we developed this model in an introduction, and then I'll move into the three main kind of sections of this presentation. So first, I'll introduce the RegionGrow3D model and its associated susceptibility framework. And then we'll kind of look at the influence of antecedent soil moisture on rainfall-induced landsliding and seismically induced landsliding. So this is probably unnecessary for this group, but you know, landslides occur worldwide and in all 50 states of the US and amount to significant casualties and losses throughout. And they also carry significant geomorphic implications. We see landslides occurring in all sorts of materials and with all sorts of different kinds of mechanisms, but today I'll be focusing mainly on shallow landslides that occur in the soil mantle. So in order to understand, what's that? Okay, I think someone's mic is just on. So in order to understand these hazards and reduce their impact on society, it's important to understand their behavior on a regional scale and from many different perspectives. And by regional scale, I just mean across large landscapes. So in this talk, I'll talk about kind of three main types of regional scale landslide assessment. Number one being susceptibility maps, which tell us about the location and likelihood of potential landslides. Geomorphic scaling laws, which tell us about their size and frequency. And landslide initiation thresholds, which tell us, you know, what magnitude of trigger do we need to cause landslides. And what these three have in common is that they're typically assessed using landslide inventories, which are databases of landslides that have already occurred in their locations. But what if we want to develop these metrics for regions where we don't have a comprehensive inventory, or for an event that we've never seen before, such as a magnitude 9.0 earthquake in Oregon, say? For these situations, we don't have landslide inventories. So to infill those data gaps, we can use landslide susceptibility models to try and predict where landslides will occur. And there are a few different approaches to landslide susceptibility, but here I'll be focusing on approaches that use physics-based slope stability models to compute where potential landslides might occur. These models can be used to create synthetic landslide inventories tied to a wide range of conditions and landslide triggering events, giving us insight into how these inputs influence regional scale landsliding behavior. But there's a catch. Landslides are pretty complex to model, so we're usually forced to make a choice. Do we employ kind of a simple 2D model such as the infinite slope, or do we go with a more complex 3-dimensional model? Well, there are pros and cons to both. So usually 2D models, they compute slope stability on kind of a single grid basis. They're fast, so you can apply them to broad regional scales easily. But they don't really do a great job of capturing the 3D physics of discrete landslide bodies. And they can underpredict landsliding in gentle terrain. So on the other hand, we have 3-dimensional models, and these can capture kind of the 3D physics of discrete landslides and more accurately model their forces. But due to their added complexity, they're typically challenging to apply at broad regional scales. So that leads me right into the motivation of this research. For this work, we wanted to develop a slope stability model that captures the 3D physics tied to landsliding, including how incipient failures can mobilize source material downhill. We wanted this model to be computationally efficient so we could apply it to large landscapes and kind of get those landsliding metrics that I talked about earlier. And we wanted to parameterize this model to capture rainfall, seismicity, and the influence of model input uncertainty, here stemming from soil shear strength. And finally, we wanted to apply this model to see how antecedent moisture conditions influence landsliding for both rainfall and seismic events. And we'll do that through a case study in the Oregon Coast Range in the Northwest region of the US. So section 1 of this presentation is about RegionGrow3D, which is a physics-based model that characterizes discrete 3-dimensional landsliding on a regional scale. So for this model, first we discretize the landscape into a grid of elevation, with each grid cell having a column of soil underneath. Then for a given set of Moore Coulomb shear strength parameters, C and phi, which define how strong the soil is, we assess the stability of each soil column using 3D limit equilibrium, which is just an evaluation of all the driving and resisting forces acting at the base of the soil column. From there, we can identify unstable columns, seen in red here, and we can cluster them together, and that represents a discrete landslide. But by definition, this landslide cluster is not in a forcive state equilibrium yet. So downslope columns of soil are added to the cluster until force equilibrium is satisfied. And this is typically accomplished by growing the landslide into less steep terrain or into deeper soil deposits that can buttress the toe of the landslide volume. We also incorporate forces from the landslide boundary using a series of soil prisms arranged around the landslide perimeter. These prisms are computed throughout the growing process for all landslides, and their geometry is defined using Rankine earth pressure angles, where the entry angle at the toe is defined by the passive earth pressure angle, and the entry angle at the crest is defined by the active earth pressure angle. And in between that, we linearly interpolate that entry angle. So from there, the driving and resisting forces of each soil prism can be evaluated using 3D limit equilibrium, and we just add that to the forces of the main landslide body. So RegionGrow3D tells us the size and location of potential landslides throughout a landscape for a given set of Moore Coulomb strength parameters. But for physics-based models, one of soil shear strength is one of the biggest sources of uncertainty, which we know is highly non-uniform, even throughout small regions. So, and it's not very practical for us to try to quantify shear strength for all the locations within our landscape. So what we do is we quantify the uncertainty in shear strength from a sample of inventoried landslides within the region. This uncertainty paired with the RegionGrow3D model serves as the basis of our landslide susceptibility framework and provides insight into not only the size and location, but the likelihood of landslide occurrence throughout the landscape. We quantify soil shear strength using a landslide forensics framework that takes an existing landslide inventory and rebuilds the 3D failure geometry for each landslide within it. Then 3D limit equilibrium is used to back calculate the shear strength of each landslide in the inventory. And using this method, we can back calculate shear strength from hundreds of landslides and summarize them using a probability distribution. And this conveys the likelihood of a range of shear strength values for a given region. I should note that in this study, we assume cohesion is 0 and that our landslides are failing in mainly frictional materials. And I should also note that this framework was developed by Michael Bunn, another one of Ben's former PhD students. But for this work, we've modified it to consider unsaturated soil conditions and both rainfall and seismic inputs. So now that we have a strength distribution for our region, we can apply RegionGrow3D for each bin of shear strength and assign each landslide distribution that corresponding probability. So when we do this for each bin and sum up all of the resulting landslide distributions, we get a susceptibility map, which represents the total likelihood of landsliding throughout the region. So now we have the susceptibility map, which is a useful tool in itself. But if we want to compute other metrics, say geomorphic scaling relationships, we actually want a synthetic landslide inventory or a distribution of discrete landslides with their own areas, volumes, and clear boundaries. So what we do is apply a susceptibility threshold, say 50% or something like that. And then we keep any grid cells that are equal to or greater than that, and we recluster them into their own discrete landslides. So for this example, if we select 40% as a threshold, we'll end up with this distribution. We could also pick 80%, and that would give us this distribution. And notice that as we increase our threshold, our landslides become not only smaller, but less numerous. And this is because our susceptibility threshold is representative of the shear strength distribution I just showed you. We can see this more clearly if we convert our soil strength distribution to a CDF, seen on the right. And without getting too in the weeds here, just note that the y-axis for the plot on the right is synonymous for our susceptibility threshold, which shows us that as you increase the susceptibility threshold on the y-axis, our friction angle or soil strength also increases. So really the main takeaway here is that a higher susceptibility threshold corresponds with higher soil shear strength. Just keep that in mind as we look at results later. So for this work, these methods are applied to about 1,000 square kilometer region in the Northern Oregon Coast Range. For this study area, we have access to high resolution topographic data from LiDAR, remotely sensed soil composition data, which we use to determine soil texture, and a high quality landslide inventory from Slido in the eastern region near the Gales Creek watershed. We define the failure surface for each soil column as the depth where colluvium or soil meets bedrock. And soil depth is computed using a nonlinear hill slope evolution model that simultaneously simulates uplift, soil production, and erosion. And this model was developed and calibrated for the Oregon Coast Range by Josh Roaring at University of Oregon, who graciously shared this code with me for this research. Antecedent soil moisture, or kind of the wetness of the soil preceding a large landslide trigger, is sourced from the soil moisture active passive, or SMAP, orbiting radiometer. This data comes in 3-hour temporal resolution for a 9-kilometer spatial resolution grid. So I downloaded about 5.5 years of this data and distilled it down to get mean soil moisture conditions for each month of the water year. The top left figure here shows the 9-kilometer SMAP grid that I used to sample this data, and the top right figure shows seasonal variations in mean moisture throughout the year for a few points in that grid, just to show some of the spatial variation. And then the probability distributions in the bottom figure shows how moisture is spatially distributed throughout the landscape for a few select months. And this is just to highlight seasonality in moisture throughout the year. So for this section and for section 2, we'll be focused on rainfall-induced landsliding. So here are the distributions of rainfall for a 2-year, 10-year, and 100-year recurrence interval. This is from the Oregon Department of Transportation. And just one thing to keep in mind is that as the recurrence interval increases in years, so do the rainfall amounts, especially in the western part of the coastal mountains where you see, kind of lighter colors. We use a hydromechanical model to bring together antecedent soil moisture, soil texture, and rainfall intensity to ultimately compute hydrologically derived stresses within our soil mantle. And this directly affects landslide susceptibility. So what this model does is it constructs an initial profile of volumetric water content and pore water pressure tied to the antecedent moisture in the soil. And then as rainfall infiltration is introduced, that profile is iteratively increased according to that infiltration. And note that soil water characteristics can change dramatically between soil types. So remotely sensed soil data is used to classify soils by texture throughout our landscape, which plays a significant role in how stresses develop during rainfall. And just as a means of validation, outputs from this framework were compared to 97 landslide points from the Slido landslide inventory. So what I did is take the landslide points shown on the left and superimpose them on a susceptibility map made using this framework. So this is for a 100-year rainfall event in January. And these inventoried points were filtered to best capture failures on natural hill slopes during a very large rainfall event that occurred during the 1996-97 winter that was known to kick off a lot of landslides in the Oregon Coast Range. I then extracted the value of susceptibility coinciding with each of these points and compiled those values into CDF seen in the figure in the top right. And note that these points were inventoried a pretty long time ago. So we noticed that many of them were not actually on hill slopes. They were kind of in valleys and other weird places. So we applied a range of buffers to these points and then extracted the maximum value of susceptibility within those buffers. So the curves in the top right show that for all buffer sizes, we see that a decent amount of these points have an appreciable amount of landslide susceptibility. And that as we increase the buffer size, these distributions shift to the right, meaning that more and more points are kind of, demonstrating higher values of susceptibility with that growing buffer. And in the lower right figure, we have buffer radius on the x-axis and a percentage of points demonstrating 50% susceptibility or higher on the y-axis. And here we also compare to susceptibility for a 2- and 10-year storm event in January. And what we see is that for the largest storm, about half the points have susceptibility greater than 50%, even for the smallest buffer. And that value increases as we increase the buffer size. Additionally, for validation, I also compared geomorphic scaling relationships derived from this framework against well-established relationships from the landslide literature. And without diving too deep here, the figures simply show that our modeled landslides show good agreement with geomorphic trends observed in real landslide inventories in terms of area, volume, and frequency. So to summarize, all these comparisons demonstrate good agreement with realistic landslide behavior and suggest that the framework here is appropriate for this kind of regional scale susceptibility modeling. So let's take a look at some actual results. So for this first section, I wanted to look at the effects of seasonality on rainfall-induced landsliding. So for the figure on the right, the x-axis shows months of the water year, and the y-axis show total field area on the left and landslide area density on the right, where landslide area density is just the total field area normalized by the total area of the study site, of the study area. And the different lines represent different storm recurrence intervals, where, as a reminder, a higher interval indicates more rainfall. And note that we've assumed a susceptibility threshold of 50% here. So the main takeaways are that for a given rainfall event, we see the most landsliding occurring in the wetter winter months, especially January and February, and that landsliding is pretty negligible in the drier months. Further, we see that landsliding ramps up more quickly in kind of in the spring, in the wetting up season, and then it ramps down more slowly in the drying season. And this is just due to kind of changes in antecedent soil moisture throughout the year. And then interestingly, we also see that landsliding is more sensitive to changes in rainfall magnitude in the winter months than in the summer months. And this is because in the winter, a lot of our storage is kind of filled up, and event rainfall can kind of go straight to work in causing landslides. And it's also worth noting that while we did model kind of these big rainfall events for the whole year, we probably would never see some of these in the summer in Oregon. But anyway, what we're seeing already is that we're starting to see that antecedent soil moisture is a crucial consideration in addition to just event rainfall. We can also look at the spatial distributions of landsliding for a given rainfall event. So the central pane here of this figure shows a distribution of landslide area density throughout the study area for a 100-year storm in February, where the colors correspond to the color bar on the right. And note that this landscape was discretized into a 240-meter resolution grid for these calculations, which you can slightly see if you get real close. The upper and lower plots show the distributions of landslide area density and slides per the number of landslides per area for each column of grid cells. And the left and right plots show the same metrics for each row of grid cells. And what this figure shows us is that landsliding is mainly concentrated in the western region of the coastal mountains, which is not only where we see steep mountainous terrain, but if you recall, it's also where we saw the most rainfall for our study area. So this just kind of adds another dimension and allows us to dial in on what might be happening locally throughout our landscape. We can look at similar plots for a wide range of rainfall events, and as you probably expect, as we increase rainfall, we see a higher degree of landslide activity throughout the landscape. So in this research, we've also proposed a modification to existing rainfall thresholds. So typically, rainfall thresholds convey that hill slopes in a given region will either fail or they won't for a certain rainfall intensity and duration. But here we present rainfall thresholds as a map, which shows us how these thresholds are distributed throughout a large region and how they might change locally or on specific terrain features. These maps are created by applying distributions of uniform rainfall, say 4 centimeters, 8 centimeters, and so on, to the landscape, running our susceptibility framework for each one, and then mapping where failure occurs. So this is an example for February, antecedent conditions, and a susceptibility threshold of 50%. But keep in mind that these maps can be created for any susceptibility threshold, representing different shear strength values. And the upper figures here show that these maps can also be used to create CDFs of these distributed rainfall thresholds, which just gives us kind of a more distilled regional scale summary of these values. Note that as we modify the susceptibility threshold or soil strength, which is indicated by the different colors, we see shifts in these distributions. And that indicates that, for low shear strength, hill slopes fail at relatively low rainfall values. And then for high shear strength, it requires a lot more rainfall to induce failure. And then just to highlight the difference that growing our landslides makes compared to a more kind of cell by cell based slope stability model, I just ran the infinite slope model and I clustered unstable cells together, which is similar to what Alveoli et al. Did in 2014. And then I compared that to outputs from RegionGrow3D, where we actually grow the landslides into a state of force equilibrium. And this comparison you see here is for February antecedent moisture conditions, a 10-year rainstorm, and a susceptibility threshold of 50%. And what we see in these figures is that in using RegionGrow3D, where we consider the downhill mobilization of source material, we can capture landslides in more gentle terrain and landslides with larger volume. So this is kind of a noteworthy contribution of this research. So just to conclude section one, we created a regional scale slope stability model that considers the physics tied to discrete landslides and the mobilization of source material downhill using 3D limit equilibrium. We've incorporated this model into a susceptibility framework that considers the uncertainty of soil shear strength inputs, and we've parameterized this model to consider antecedent soil moisture and extreme rainfall events. And this framework allows us to kind of quantify those regional scale landsliding metrics where we may have lacked sufficient inventory data otherwise. So section 2. So now in section 2, we'll apply this framework to look at the relative influence of antecedent moisture on rainfall-induced landsliding behavior at the regional scale. So for this section, we compute a new set of antecedent moisture conditions. The approach is similar to that of section 1, but instead of just computing mean conditions for each month, we also consider conditions on a relatively dry year and a relatively wet year. This is done by computing the standard deviation in daily remote sensed volumetric water content from SMAP for each month, and then adding that standard deviation to the mean moisture for wet conditions and subtracting it from the mean moisture for dry conditions. So if you look at the upper right figure here, the solid lines show you mean moisture throughout the water year, and the two boundaries on the shaded region kind of show you wet and dry conditions. And then this bottom figure shows you the spatial mean of kind of the whole study area for dry, mean, and wet conditions for each month of the water year. So let's take another look at the seasonal effects of antecedent moisture on landsliding, but this time considering mean conditions as well as relatively dry and wet conditions as well. In this figure, we have similar curves as what we saw in section 1, where the different line types represent different storm occurrence intervals. However, we also have different colored curves, and those represent conditions on dry, mean, and wet moisture years. So at first glance, we see many of the same trends we saw in section 1 of this presentation, but now we see some new interesting behavior as well. Note that there are locations, especially in the wetter months, where curves of different colors cross over each other. These crossovers indicate cases where the largest magnitude rainstorm may not produce the highest degree of landslide activity if we have relatively dry conditions. And conversely, we see that smaller storms may produce more landsliding if antecedent conditions are, relatively wet. So for example, we see that in February, a 10-year storm during wet conditions may produce higher landslide area density than a 100-year storm during dry conditions. And this highlights kind of the important role that preconditioning plays in landsliding during these large rainfall events. And again, we can look at the spatial distribution of landsliding, this time for a 10-year storm in February. and a susceptibility threshold of 50%, and kind of a range of antecedent moisture conditions. And what we see is a similar spatial trend in the distribution of landslide area density as we saw in section 1, where elevated landslide activity is kind of concentrated in the steeper terrain and where rainfall is the highest in the west. However, we see here that the distribution of these metrics increases as we go from dry to mean conditions and from mean to wet conditions. And further, we see that trends in landslides per area closely follows those of landslide area density. And that indicates that, while landslides are getting larger, we're also seeing more of them, and they're becoming more numerous. So here, again, we have spatial distributions of rainfall thresholds for February and a susceptibility threshold of 50%. So the map in the upper left corner kind of shows thresholds for the entire study area for mean conditions. And that little black box in there kind of just shows what we're seeing in panes, B, C, and D there, which is what we'll be focusing on to kind of look at these relative changes in thresholds. So part B of this figure shows thresholds for relatively dry conditions. And notice that much of the map is gray, meaning that slope failure hasn't occurred for kind of the range of rainfall that we've considered here. We see that some hill slopes have failed, though most require very high levels of rainfall. As we increase our antecedent conditions to mean conditions, we see that much more of the landscape has failed, and some areas have turned blue, indicating that failure is occurring at lower rainfall amounts. And then this trend just continues as we move from mean conditions to wet conditions, where we see much of the landscape, even gentle terrain, has failed for high levels of rainfall. And kind of on the steeper slopes, we're requiring less and less rainfall to cause failure. And in this section, we also look at geomorphic scaling laws for a range of rainfall recurrence intervals, antecedent soil conditions, soil moisture conditions, and susceptibility thresholds. So let's first focus on this figure on the left, which shows scaling laws for February and a susceptibility threshold of 50%. The left three plots here show landslide area on the x-axis and frequency density on the y-axis. And these curves convey just kind of how many landslides exist within our landscape for the range of areas shown. And note that each row of this figure represents different rainfall recurrence intervals, which is labeled on the left. And the different line types represent different antecedent moisture conditions. So here we can see that as we increase rainfall magnitude from the top pane to the bottom pane, our curves shift upward, indicating that more landslides of all sizes are occurring. Also as we move from dry to wet conditions for each rainfall event, we see an upward shift there as well, with this shift being kind of the greatest for our 100-year storm. The three plots on the right show probability density, which is simply frequency density normalized by the total number of landslides that have occurred. And these plots show us that as we look at larger rainfall events and kind of shift towards wetter antecedent conditions, we see the right side of these curves kind of kick upwards. And this indicates that we're seeing an increased proportion of large landslides with wetter conditions and with more rainfall. And so now if we look at the relationships here on the right, the difference in colors represent changes in shear strength. And the main takeaway here is that as we reduce shear strength, we see a significant shift in the number of landslides occurring. And we also see our distributions, again, shifting towards larger landslides. So to conclude chapter 2, we've seen that relative differences in antecedent moisture can play a significant role in rainfall-induced landslide behavior. We can get more landsliding during dry conditions with a large enough rainfall event, and vice versa. It may not take as much rainfall to cause a large landsliding event if antecedent conditions are especially wet. And we've seen that soil strength and antecedent soil moisture can shift geomorphic scaling relationships significantly. So in this final section, Section 3, in this final section, we'll modify RegionGrow3D to assess seismic slope stability through a pseudostatic approach. And similar to the previous section, we'll look at the influence of antecedent soil moisture on coseismic landsliding. So in this chapter, RegionGrow3D is modified to consider seismic acceleration in the form of a pseudostatic coefficient in the direction of sliding. These additional accelerations effectively increase the driving forces within the landslide, and they also reduce the normal forces, the normal force acting on the landslide failure interface. And that ultimately reduces resisting forces. And the result of these two things are kind of a general decrease in hill slope stability. And while there are a number of additional processes occurring in the soil during shaking, this approach is a relatively simple means of approximating the influence of earthquakes while kind of retaining RegionGrow3D's efficiency. So as an input, we're using modeled peak ground accelerations, or PGA, generated by a large fault off the west coast of Oregon called the Cascadia Subduction Zone. These modeled values that you see on the right were developed as part of the Oregon Resilience Plan, and these figures on the right kind of show some different examples of different magnitude earthquakes. And just for reference, note that for Cascadia, earthquake magnitude is linked to rupture length going from south to north along the fault, and that our study area is actually located in northwestern Oregon. So just keep in mind that the results of this section would probably look very different if we were somewhere else, like the southwest corner of Oregon. But that being said, here are maps of peak ground acceleration for a magnitude 8.1, 8.4, and 9.0 earthquake, cropped down to the size of our study area. And again, we can look at the seasonal influence of moisture, but this time for coseismic landslides. Note that we see similar trends in landsliding behavior to what we saw in the first two sections, but there are also some unique takeaways here. The most notable being that during the wettest months, regardless of antecedent soil moisture, a magnitude 9.0 earthquake is shown to pretty much always take the cake, and and always produces kind of the highest degree of landsliding for this area. And another important takeaway is that we see significantly more landslides for earthquakes in the winter than in the summer. And while this has probably been intuitive to planners for a long time, a susceptibility framework such as this kind of allows us to quantify these relative changes for a given region. And then here again, we see spatial distributions, the landslide area density and slides per area for a magnitude 9.0 earthquake during the month of February. This is for a susceptibility threshold of 50%. And the map in the middle shows PGA for a 9.0 earthquake. And again, the different colored curves represent dry, mean, and wet conditions. And what we see here is that as we increase relative antecedent moisture, there's an increase in landslide area density and slides per area throughout the landscape, especially in the western region of the coastal mountains. We also see that as we move eastward, kind of our landsliding activity dissipates. And as opposed to our rainfall-induced landslides, this is due not only to the presence of steep terrain, but due to our proximity to the Cascadia Subduction Zone, which we kind of move away from as we go east. And one of the most common forms of initiation thresholds for seismically induced landslides is the yield acceleration, which is just the seismic acceleration at which a slope fails. And it's usually presented as kind of a single value, that goes with a single slope. For my master's thesis, I developed 2D distributions of yield acceleration for single hill slopes. But regional scale maps of yield acceleration have yet to be developed as far as I know. So here, similar to what we did in section 2, we apply uniform distributions of PGA in increments to the landscape, and then we map the yield acceleration when landsliding occurs. These results are for dry, mean, and wet moisture conditions for a subregion of the study area. And what we see is that for dry conditions, we see that much of the landscape requires a very high acceleration to fail. Some of the steeper hill slopes exhibit failure for accelerations around 0.5 Gs, but that's still pretty high. And as we increase the moisture from dry to mean and from mean to wet, we see that failure becomes more widespread at very high accelerations, and that steeper hill slopes begin to fail at lower accelerations. And this type of analysis just allows us to kind of relate our knowledge of expected ground accelerations to specific locations or terrain features in our landscape. So we can kind of dial in on those. So here again, we have geomorphic scaling laws for February and a susceptibility threshold of 50% for coseismic landslides. And if we start with the figure on the left, we have frequency density for the left three figures and probability density for the right three panes. And we have different earthquake magnitudes corresponding to each row. And what we see here is that as we increase earthquake magnitude, our frequency density curves shift upward, indicating that more landslides are occurring throughout the region. And similar to what we saw for rainfall-induced landslides, we see another shift upward as we go from drier to wetter antecedent moisture conditions. Also note that at the right side of the probability density curves, we see a shift towards larger area landslides as earthquake magnitude increases, but this shift seems to be less sensitive to changes in antecedent moisture when compared to our similar curves for rainfall-induced landslides. Now, if we look at changes in these relationships tied to our susceptibility threshold or soil strength for a magnitude 8.4 earthquake in February, we see that for all antecedent moisture conditions, landsliding behavior is highly sensitive to changes in shear strength. And this shows that for coseismic landslides, frictional shear strength may play a more influential role in stability, since we're mainly considering kind of just an additional inertial force as opposed to rainfall, which can really wet up the landscape and even saturate it. And then finally, for this chapter, for this section, let's just look at a comparison of landslide area density tied to both rainfall and seismic events, just to bring them together. So first off, note that each part of this figure corresponds to a different susceptibility threshold or shear strength. The y-axis is landslide area density, and the y-axes represent uniform distributions of rainfall and uniform distributions of PGA. The solid lines correspond with the bottom x-axis or PGA, and the dashed lines correspond with rainfall for the top x-axis. And these different colors are for different antecedent conditions. So there are a couple of interesting takeaways here. The first being that for some shear strengths, we see curves tied to different disturbances crossing each other, which suggests that there are a number of combinations of antecedent conditions, PGA, and rainfall that may produce kind of the same value of landslide area density. So for example, we see that for T equals 60 in pane C, the 18 centimeters of rainfall during dry conditions and 0.15 Gs of seismic acceleration during wet conditions both produce landslide area density of about 0.01. And we even see that some of these relationships cross each other twice due to their nonlinearity. We also see that as we increase soil strength, the maximum value of landslide area density doesn't change much for very high levels of rainfall. However, we see that shear strength does seem to put a cap on coseismic landsliding, at least within the bounds we've looked at here. This is likely due to rainfall's ability to kind of raise pore pressures and in some cases cause full saturation of the landscape, which can significantly reduce resisting forces in the soil. So just as a conclusion for section 3, RegionGrow3D was modified to model coseismic landslides. We saw that antecedent soil moisture conditions play a significant role in coseismic landsliding. And Further, we saw that coseismic landsliding is sensitive to seasonality and tends to be concentrated in the western part of the coastal mountains for this study area, where we're closer to the Cascadia subduction zone. We looked at maps of yield acceleration, conveying, what values of PGA are required to fail hill slopes throughout our study area. And finally, we compared landslide activity for a range of antecedent moisture, shear strength, and rainfall and seismic triggers, which showed us that different types of triggers may produce similar amounts of landsliding, depending on our soil strength and antecedent moisture. And so with that, I'd just like to thank Ben Lashinsky at OSU, who advised me throughout the development of this work, Oregon Department of Transportation, who funded the kind of initial development of this model, my PhD committee and co-authors from September, Ben Meares, Adam Booth, Mike Olson, Matt Evans, Francisca Ballart, and Josh Roaring for sharing his geomorphology expertise and his hill slope evolution code with me. And with that, thank you so much for your time. And yeah, thank you.